Okay, in this video, I'm going to show you how you can use the properties of natural logarithmic function to solve other problems involving compound interest, different from the ones we've seen before. Because in these problems, we're given all the information except the unknown is time. We want to find out how long it will take for our investment to increase to a certain amount, given the initial amount, the interest rate, and how often per year it's being compounded, whether it's a certain number of times per year, for which we use this formula, or continuous compounding, in which case we use this exponential. So I'm going to show two problems, one with that's not continuous compounding and one that is, to show you how to solve for the amount of time it takes for the balance to reach a certain amount. So in this first scenario, our initial deposit is $14,000. We want to see how long it takes this money to double. So in other words, we want to see how long it'll take to get to $28,000. We have a 6.5% interest rate, it's an annual rate. And the number of times interest is compounded per year, it's semi-annual, so twice per year. So n is equal to 2 in this formula. And then time is our unknown. We want to see how many years it takes for this deposit to double in size. Okay, so now what we can do is substitute all the numbers that we know into that formula. So what we get is our final balance is $28,000. That's equal to $14,000 times 1 plus the rate, the interest rate, so as a decimal, 0.065 over 2 for compounding twice per year to the 2t. So number of times per year goes here in the denominator and also in the exponents. Now we need to solve this equation for the only thing that's unknown, and that is t. First thing you do, divide by the initial balance. So divide both sides by 14,000. And then we cancel out on the right side. On the left side, we just get 2. So what the end of on the left side is always the amount by which you wish to increase your initial deposit. We want to double our money, so that's going to be 2 in this case. So the amount of time it takes to double your money is independent of how much you put in the first place. So that's one interesting point to make. That we could have just dispensed with knowledge of the principle and just had 2 here, and that is equal to 1 plus 0.065 divided by 2, so that's going to be 1.0325 after working out what's in parentheses here to the 2t. Now, in order to be able to solve for t, what we need to do is take the natural logarithm of both sides. So we have natural log of 2 is equal to natural log of 1.0325 to the 2t. But now we can use one of the properties of a natural logarithmic function, and that is a log of a number raised to a power is equal to that power times the log of that number. In other words, the exponent can be pulled down. So I have natural log of 2 is equal to 2t natural log of 1.0325. And now I'm in a position to solve for t. I couldn't really do that before. So if I divide both sides by 2 and natural log of 1.0325, I can get a formula for t. So it's a natural log of 2 over 2 times the natural log of 1.0325. Now what you can do is work that out on your calculator, and we'll round this to 2 decimal places. So I have, okay, I'm actually going to work out the denominator first because there's more in it. So I have 1.0325 natural log times 2, and then 1 over x times 2 natural log, and I get, rounded to 2 decimal places, 10.84 That's how long it'll take for whatever amount of money you put in initially to double at that interest rate, that rate of compounding. Okay. So in general, the formula for t is going to be natural log of, I'll call it s. S is the scaling factor by which you want your money to increase. So in this, since we're doubling, in this case s equals 2. But if I wanted to increase by tenfold, I'd put 10 in here. So natural log of s over n, natural log of 1 plus r over n. Okay, so this is a formula in general for figuring out how long it takes for any amount of money to increase by a certain factor s. Okay, now for a second scenario, we need a different formula because now we're compounding interest continuously. So we're using a equals p e to the rt. We don't have an n in this case because n is effectively infinity. So here are numbers this time. So we have, I'm going to take advantage of the fact that we're doubling. So we don't really need to work with the initial amount. It's just going to be 2, whoops. 2 is equal to e to the rt. R is 0.095, expressed as a decimal, times t. So now I can solve this equation for t, but first I need to take the natural log of both sides, like before. Natural log of 2 is equal to natural log of e to the 0.095t. The exponent I can pull down. It's 0.095t times the natural log of e. But natural log of e is equal to 1. So I can forget about that. And now I can solve for t. T is equal to natural log of 2 over 0.095. Okay, so now I can turn to my calculator, and so I have 2 natural log divided by 0.095. And what I get to 2 decimal places is 7.30 here. So that is my final answer in that case. So in general, the formula is t is equal to natural log of, again, whatever multiple of your money that you want. If you want to increase it by a factor of 2, this would be 2. Or increase it by tenfold, you put a 10 in here. Divided by r. So it's a simpler formula in this case for continuous compounding than when it's not.